So let's just do a little example of multivariate optimization. And let's take this function of two variables, x1 and x2, for x1 squared minus x1, x2 plus 2x1, x2 squared. And let's say our task is just to find local extreme values. So just as we talked about in the last lesson, we're going to find values of x1 and x2 that satisfy the first order conditions. We're going to form the Hessian, and we're going to evaluate the Hessian at our critical points to classify them. So FOC1 says that the derivative of f with respect to x1 has to equal 0. And what is that derivative? Well, it is hx1 minus x2 plus 2x2 squared. And FOC2 says that the derivative of f with respect to x2 also has to be 0. Okay, and so same deal, take the derivative of that thing, but now we're treating x1 as a constant and differentiating with respect to x2. So derivative of the first term is 0. The derivative of the second term with respect to x2 is negative x1 plus 4 x1, x2. Okay, so these two things have to be equal to 0. Now I just need to find the values of x1 and x2 that make both of these things true, and I'm just going to kind of solve them sequentially. So in a way, we're going back to these very basic skills that you guys worked on in Unit 1. So I'm going to switch colors here to do my solving. In green, going to first just look at the second first order condition, which I'm going to rewrite as x1 equals 4x1, x2. And I'm going to observe that this is true if x1 equals 0, right? That would make it true. If x1 doesn't equal 0, I can divide it out. And in that case, I'm left with 1 equals 4x2. So the other thing that can make it true is x2 equals 1/4. Okay, so two cases to think about here. Okay, so let's call this case A and case B. So if we're in case A, and now we look at the other first order condition, because that has to be satisfied as well. So we're in this case here, we know that x1 equals 0. Plugging that in to FOC1, I get 0. FOC1 implies that I get a 0 here, negative x2 plus 2, x2 squared equals 0. Again, I can rewrite that as x2 equals 2x2 squared. This is true if x2 equals 0, or if x2 equals 1/2. So I have two critical points. Zero, 0, and 0, 1/2. Okay. Those come from solving the second first order condition, seeing that there were two possible things that could make that true. Looking at the first one, x1 equals 0, there were two values of x2 that would make this first order condition true here. And then see if I have space to put in my case B here. If x2 equals 1/4, putting that into FOC 1. Okay, I get 1/4 times 8. It's 2. Oh, except it's x2 equals 1/4. Let me just draw your attention to that. The two ways that this could be true, one told us a value for x1, the other told us a value for x2. So let's be careful about that. This is saying that 8x1 minus 1/4 plus 2 1/16 equals 0. Okay, that is 2/16 is an eighth. That is the same as 8x1 minus 1/8 equals 0. That sounds like x1 equals 1/64. Okay, so I had two critical points here for my first case, and I have one more critical point here, which is 1/64. 1/4. All right. Let's see if I can bring some of my work over to the next page. If this doesn't work, I'll just recopy it. But I want to remind myself of what the first order conditions are, and these first derivatives are. Okay. So let's see if I can get it to paste over here. Oh, how cool is that? All right. The other thing I think I want to remind myself while it's still fresh is we found 3 critical points. Okay, we found that when x equals 1 and x1 equals 1 and x2 equals 0, the first order conditions are satisfied, both of them. When x1 equals 0 and x2 equals 1/2, and when x1 equals 1/64 and x2 equals 1/4. Okay. So that was kind of my working out the little details color. Let's go back to kind of the main narrative. The second step now is we want to classify the critical points with the Hessian matrix. Okay, so this is why I wanted to copy my first derivatives, because I need to take their derivatives to find the Hessian here. So remember what I'm looking for here is the direct second partials on the main diagonal and the cross partials on the off diagonals. So for this function, the second derivative with respect to x1 both times, that's the derivative of the first derivative both times with respect to x1, that is 8. So here, my f11 is. Let's just go ahead and do the other direct second partial. So taking the derivative of del f del x2 with respect to x2 again, I get 4x1. And now I need to do the cross partial here. So taking the derivative of del f del x1, this time with respect to x2, I get -1 plus 4x2. Okay, that's differentiating this with respect to x2. Let's just make sure that I'm doing it right and differentiate del f del x2 with respect to x1 and see if I get the same thing. And indeed, I'll get -1 plus 4x2. Okay. So now to classify the critical points, I need to evaluate the determinant of H at each of these critical points. So let's do that. h of 0, 0 is 8, 0, negative 1, negative 1. So the determinant of h is 0, minus 1, negative 1, 0, 0 is a saddle point. H of 0, 1/2, that is 8, 2, 1, 1. Oh, sorry. It's not 8, 2, 1, 1. It's 8 is always there. That's a constant, but 4 times 0 is 0. Yeah. The x2 equals 1/2 does mean that we have the ones here. So again, we have a determinant that is 0, minus 1, the fact that it's less than 0. Again, we have a saddle point. What a bummer. We're coming up with all these saddle points. And then the final possibility for h, can we find anything that really is a local min or max here at x equals 1/64, x1 equals 1/64, x2 equals 1/4. It's going to be 8. 4/64 is 1/16. 1 minus 4x, 0, 0. Okay, so the determinant, 8 times 1/16 is 1/2 minus 0. Determinant of h is 1/2. That is greater than 0. Okay, so it's not a saddle point, and my both of my direct partials are positive. So could have just as easily written FYY there, but we can conclude that 1/64, 1/4 is local min. So you'll have a chance to do a couple of problems like this in practice problems. The thing I want to point out to you kind of at the end here is a lot to some of these steps, like the most tedious part of this problem, maybe tedious isn't even quite the word, but the place where like I would be most likely to make a mistake is not in the calculus. It was in the bit that was in green here of just kind of doing the basic algebra to find those critical points. So that tends to be true in any kind of multivariate topics. There's a lot of little steps involved, but the macro structure is not all that complicated. So find those places where the function is not increasing or decreasing in any of its dimensions, those critical points, and then look more closely at the shape of the function, that is, look at the second derivative, right at those critical points to figure out what's going on there. And that's how we do it.